Pain. We've all felt it. But have you ever really thought about how it works? I mean, what's actually happening inside our bodies? Today, we are going to do a deep dive into narcotic analgesics. But to truly get a handle on them, we have to start right at the beginning. We're going to follow the incredible journey that a single pain signal takes from a simple injury all the way up to your brain. So here's our game plan. First, we'll trace how a pain signal even gets started and makes its way to the spinal cord. Then, we'll follow it as it climbs up into the brain to see how it's actually processed. After that, we'll look at the body's own amazing built-in pain control system, which is crucial because that's the system that narcotic analgesics tap into. Then, we'll finally get to the drugs themselves, see how they affect the whole body, and wrap up with how we manage their powerful effects. All right, let's get started right at the source. Just imagine you've stubbed your toe. How does that initial ouch transform from a physical event into an electrical signal that starts racing towards your central nervous system? Let's break it down. This image right here is basically our roadmap for the first part of this whole story. If you look over on the left, that's what we call the periphery. Think of it as your skin or a muscle. When there's an injury, say from heat or pressure, the damaged tissue releases this whole cocktail of chemicals. Now, these chemicals, they don't just float around. They activate the very end of a specialized nerve. And that activation creates an electrical signal. That's our pain message, which then shoots down the nerve fiber toward the spinal cord. And from there, as you can see, it gets relayed all the way up to the higher centers of the brain. We're going to unpack every single step of this incredible journey. Okay, let's zoom in on that very first moment. It's a really clear chain of events. The cause is some kind of harmful stimulus, a cut, a burn, something that injures the tissue. The immediate mechanism is the release of what you could call an inflammatory soup of chemicals from all those damaged cells, mast cells, and neutrophils. We're talking about things like histamine, bradykinin, 5-HT, prostaglandin, and ATP. And here's the crucial consequence. This chemical soup sensitizes these specialized pain receptors called nociceptors. You can think of them as the body's alarm sensors. Once they're activated, these nociceptors fire off their own set of chemical messengers, like substance P and calcitonin gene-related peptide, or CGRP, to carry that pain signal onward to the dorsal root ganglia and then right into the spinal cord.
Now, this is really cool because it explains why pain can feel so different at different times. See, not all nerve fibers are created equal. You've got these big, fast, myelinated A-beta fibers, and they're mostly just telling your brain about normal touch and pressure. Then you have the smaller A-delta fibers. They're still pretty fast, still myelinated, and they're the ones responsible for that initial, sharp, I know exactly where that is, kind of pain, like when you get a paper cut. But that throbbing, dull, widespread ache that comes later, well, that's the work of the very slow, small, unmyelinated C fibers. And as you can see, even they come in two different flavors, peptidergic and non-peptidergic, which just adds another layer of complexity to the signals our brain has to sort out.
Okay, so our pain signal has made it from this site of injury, and it has just arrived at the spinal cord. But its journey is far from over. Now it has to be processed and relayed up to the brain, our central command center, where all this raw electrical data is finally interpreted into the complex experience that we call pain. So the spinal cord isn't just some simple cable. No way. It's a really sophisticated processing hub. The pain signal arrives in a specific area called the dorsal horn, which is organized into these distinct layers, or laminae. And different nerve fibers actually connect to different layers. Lamina I, for example, is a key receiving station for that nociceptive information. But look at lamina 2. This area is absolutely critical for modulating and integrating the pain signal. And here's a detail that's going to be incredibly important in a few minutes. Lamina 2 is packed with opioid receptors. This is one of the key places where our body, and the drugs we're about to talk about, can step in and turn the volume of that pain signal way, way down. Laminae 3 through 5 are also involved, transmitting these signals onward while mixing in other sensory information. All right, so from the spinal cord, the signal begins its climb to the higher brain. It travels up through the brainstem, and it passes through several critical checkpoints along the way. The parabrachial nucleus, for instance, processes the signals before passing them on. But places like the periaqueductal gray, or PAG, and the rostral ventral medulla, or RVM, are fascinating because they are part of the brain's descending control system, meaning they can actually send signals down to block incoming pain signals right at the spinal cord. We'll definitely come back to that. Finally, the signal arrives at the thalamus, which basically acts as the brain's central switchboard, directing all kinds of sensory information to its final destination. And this is where it all comes together. The signal leaves the thalamus and spreads out to different parts of the cortex. And this is why pain is so much more than just a physical sensation. The somatic sensory and insular cortices, they're the parts that answer the simple sensory discriminative questions. Where does it hurt and how bad is it? But the cingulate cortex? That's responsible for the emotional processing, the suffering, the unpleasantness of it all. And the amygdala gets involved in the emotional response, that fear and anxiety that can make pain so debilitating. So you see, it's not just a signal, it's a deeply unpleasant experience. Now, before we even start talking about drugs like morphine, we have to understand something pretty amazing. Our bodies have their own built-in system for controlling pain. This system uses its own natural opioid molecules and receptors. And it's this very system that narcotic analgesics are designed to tap into, or, as you'll see, to hijack. You see, our body makes its own morphine-like molecules. We call them enkephalins, dynorphins, and endorphins. And they act on a family of 4 main receptor types. Let's meet them. The mu receptor is the big one. It's the primary target for pain relief. But it's a double-edged sword. It's also responsible for the euphoria, physical dependence, and the really dangerous side effect of respiratory depression. The delta receptor helps modulate our emotional responses to pain and also chips in with analgesia. The kappa receptor can also reduce pain, especially that deep, visceral pain, but activating it can cause sedation and make you feel really awful, a state we call dysphoria. And finally, the NOP receptor plays a more complex role in pain modulation and stress. Understanding these different receptors is absolutely key to understanding why opioids have such a huge range of effects. So how do these opioids actually stop a pain signal at the cellular level? Well, it's a brilliant 2-part mechanism. First, an opioid molecule binds to its receptor, which is a specific type called a G/GO coupled protein receptor. This kicks off a chain reaction inside the cell that shuts down a key enzyme called adenylyl cyclase, which in turn drops the levels of a messenger called CAMP. Now, here's the double whammy effect this has on the neuron. On the postsynaptic side, that's the one receiving the pain signal, this action opens up special potassium channels. Potassium rushes out, making the inside of the cell more negative. This is called hyperpolarization, and it makes the neuron much less likely to fire. At the exact same time, on the presynaptic side, the one sending the signal, it blocks calcium channels. Without calcium coming in, the neuron can't release its excitatory neurotransmitters like glutamate and substance P. So the end result is the same. In both ways, the pain signal is effectively stopped dead in its tracks. Okay, so we've seen the body's natural pain control system. Now we're ready to see how pharmaceutical opioids, the narcotic analgesics, work by tapping into and amplifying this very same system to produce their incredibly powerful pain-relieving effects. And it all begins right here with this plant, the opium poppy, Papaver somniferum. From its juice, we get morphine, the original and most famous narcotic analgesic. Now, take a look at these chemical structures. This is fascinating. A key part of the morphine molecule is structurally very, very similar to tyrosine, which is an amino acid that forms the tip of our body's own natural endorphins. It's like a key that just happens to fit perfectly into a lock that nature already built. And that's why it binds so powerfully to our opioid receptors. You can also see how other drugs, like heroin, which is just an acetylated version of morphine, and the overdose reversal drug naloxone, are all just slight chemical modifications of this original structure. So from that natural starting point, chemists have created this huge family of synthetic and semi-synthetic opioids, often trying to make pain relief stronger with fewer side effects. You've probably heard of a lot of these: fentanyl, oxycodone and its relative oxymorphone, hydrocodone and its relative hydromorphone, and meperidine. At their core, they're all potent activators, what we call agonists, of that key mu opioid receptor. Some, like codeine, are kind of clever prodrugs, meaning your body has to metabolize them into morphine before they can work. And then you have others, like methadone, which are unique because they are both a mu agonist and an NMDA receptor antagonist, giving them special properties for managing certain types of pain and addiction. This diagram perfectly illustrates the powerful 2-pronged attack that makes opioids so incredibly effective. They don't just work in one place. They work at both the supraspinal or brain level and the spinal level. So up in the brain, in those centers we mentioned earlier like the PAG and RVM, opioids actually enhance the brain's own descending inhibitory pathways. They basically turn up the brain's off switch for pain, increasing the release of serotonin and norepinephrine down in the spinal cord to block signals there. And at the very same time, down at the spinal level, they act directly to inhibit the ascending pain signals from ever getting up to the brain in the first place by reducing C fiber activity and neurotransmitter release. It's an incredibly effective dual strategy, amplifying the off switch while simultaneously jamming the on switch. But as anyone who knows about these drugs is aware, powerful pain relief is only part of the story, because opioid receptors aren't just in the pain pathways, they're all over the brain and the body. And this means these drugs have widespread and often dangerous effects that go far beyond just analgesia. This table is a fantastic summary that connects specific effects to specific receptors. Just look at the row for the mu receptor. You can see it's responsible for the analgesia we want, but it's also linked to the most dangerous side effects, respiratory depression and physical dependence, not to mention euphoria. This is really the central dilemma of opioid pharmacology. In contrast, look at the kappa receptor. It's strongly linked to negative feelings like dysphoria. This is exactly why drug developers are so interested in creating medications that can selectively target just one receptor type to try and get that pain relief without all the unwanted baggage. Okay, let's break down some of these key effects on the central nervous system. That intense euphoria or dysphoria, that comes from mu and kappa receptors in the brain's reward center, the nucleus accumbens. The sedation or drowsiness happens because opioids enhance the activity of the inhibitory neurotransmitter GABA. The most lethal effect, respiratory depression, is caused by mu receptors in the brainstem's medulla, making the body less sensitive to rising carbon dioxide levels, basically making you forget to breathe. On a less dangerous note, they're great cough suppressants by acting on the medullary cough center, which is why codeine is in some cough syrups. They can also trigger nausea and vomiting by stimulating something called the chemoreceptor trigger zone, also in the medulla. And they cause the pupils to constrict to tiny pinpoints, a classic sign paramedics look for in an overdose, caused by stimulation of the oculomotor nucleus. And the effects aren't just in the brain, they extend right down into the gastrointestinal tract. Opioids are notorious for causing severe constipation because they increase the tone of the smooth muscle but drastically reduce motility, slowing everything down. They also cause the biliary sphincter to constrict while making the gallbladder contract, which increases pressure in the biliary system. And this leads to a really important clinical note. You should avoid giving an opioid to someone having a gallstone attack, what's called biliary colic, because it can paradoxically make their pain dramatically worse. So, given this whole host of powerful effects, both the good and the bad, a huge part of using opioids clinically is about managing them. In our final section, we'll look at the drugs we use to reverse opioid effects and some of the strange complications that can pop up with long-term use. To fight back against opioid effects, we use drugs called antagonists. There are a few key types. First, you have the pure antagonists, like naloxone and naltrexone. Think of them as molecules that just rush in, kick the opioid off all the main receptors, mu, delta, and kappa, and then block them completely, which is how they can rapidly reverse an overdose. Then you have the really clever peripherally acting mu antagonists, like methylnaltrexone, alvamopan, and naloxegol. They're designed so they can't cross the blood-brain barrier. So what does that mean? It means they can go to the gut and reverse constipation without taking away the pain relief happening in the brain. Finally, you have partial mu receptor agonists, like buprenorphine. It only sort of tickles the receptor instead of fully activating it. This provides some effects, but has a ceiling, which means it's much harder to cause life-threatening respiratory depression. That makes it very useful for treating opioid addiction and managing withdrawal. Now, here's one of the great paradoxes of long-term opioid use. In some people, instead of decreasing pain, the drugs can actually wind up the nervous system and make it more sensitive to pain. This bizarre phenomenon is called opioid-induced hyperalgesia, which means an increased intensity of pain and an altered pain threshold. As this graph can show, the normal pain threshold drops, and you can even get to a point called allodynia, or something that shouldn't hurt at all, like a light touch, becomes painful. It's a huge clinical challenge. Management can involve something called opioid rotation, switching to a different opioid like methadone, or co-administering adjuvant drugs like ketamine, which is an NMDA antagonist, to try and calm that oversensitized nervous system back down. And this brings us to a really crucial takeaway. We've seen how incredibly effective opioids are because they target the body's natural pain pathways. They're life-saving for severe acute pain and for cancer-related pain. But for many types of chronic, non-inflammatory pain, which might be caused by a nervous system that has become dysfunctional, they often fall short. The pain isn't just a signal that needs to be blocked, it's a disorder in and of itself. And this reality is what leaves us with that final important question. It's pushing medicine to look beyond traditional painkillers towards a future where treating chronic pain may require using a completely different set of tools, like antidepressants or antiepileptics, to fundamentally retrain the nervous system itself.